Okay, so I'll send you tomorrow the study guide for the exam. So remember, like, our next exam is next Wednesday of next week, right? Like before the spring break. We're mostly done. It is whatever I finish covering on Wednesday, like that would be the last day of like topics. But I'm waiting to see how much I do today because once I know that, like I have a pretty good sense of what it would be, um, what I would be able to talk on Wednesday. Basically, whether I'm including like one section about series or not. Like that's all like that I'm trying to figure out. Um, let me see. Okay. So yes, I was saying today we'll talk about sequences and series, which is actually a really nice topic. I feel like in this class, like series is like really interesting. But let's start with sequences because we do need to have like some basic understanding of what that is. So like, on a very like kind of like as an initial definition, like, a sequence is just essentially like a list of numbers. Okay. A sequence is a list of numbers. But that list does have an order, so it is listed in some way. Uh, so it is listed using like the natural numbers, okay? Or like if you prefer, like by that I just mean like positive integers. So for example, let me just write a few examples of this, what I mean. Like this is kind of like things that like you could like these games in newspapers where like you're just trying to find the pattern to the list of numbers. So you have like 1, 2, 4, 8, 16, 32, what it would be next, 64, blah blah blah. In this case, like the way I'm writing it, I want to like again, it is listed with a particular order. So it matters that 1 is the first element in the sequence, 2 is the second element, 4 is the third element. So just to emphasize that a little bit better, this is called A1, this is called A2, this is called A3, this one is called A4, A5, A6, A7, right? And well, hopefully in this particular case, you can see that, like basically the way I'm thinking about the next term is just dot twice the previous term, right? So I'm just multiplying by 2 to get to the next element. So, usually the way sequence is presented, like more as a formula, right? In this case, it would be kind of like a sub n. So what would be it has to be a power of 2, right? Because it's like certain like the number 2 a certain amount of times. If you kind of see here, um, well, maybe I could write them. Let me before write the formula, I'll write everything as a power of 2 below so that it's a bit more clear. So what is 1? That's 2 to the 0. What is 2? That's 2 to the 1. What is 4? That's 2 squared, right? 8 is 2 cubed. 16 is 2 to the 4, 32 is 2 to the 5, and the other one, 64, is 2 to the 6, right? So if you write if you write every element in the sequence as a power of two, what you'll see is that basically, you know, this like the exponent, right? The exponent and the look at the or like the the moment in which the element appears, they're basically related and they're just like differ by by one, right? So essentially the element in the nth position is just 2 to the n minus 1, right? And here like n could be for n is 1, 2, 3, 4, 5, 6, blah 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 blah. It goes on for that. Okay, that making sense. So far, so good. How I wrote it. Yeah. Also, I mean, like right, like the convention is like that that so this is called the end here is called the index, right? Like that is what the label that you give to the number, right? So the convention is that that the what carries the label is like a natural number. So yeah, it wouldn't be it wouldn't be negative, right? Because in a sense, like kind of like the idea is that you should think of like a sequence as a list that goes an infinite list, but just in one direction. Not kind of like going in, if you had like a list which is kind of like 0, 1, 2, 3, but also -1, -2, -3, like kind of like spreading out in both directions, then in that case, it would be more natural to kind of like do it with the integers. But usually the way we think about the sequence is more like you start with a with a number, and then there's a second number, there's a number followed by it, et cetera, et cetera. And so like in that case, it's the most natural. Correct. Exactly. Like that's a good point. Like yes, like you could have like here's like a well no this is like this actually would have been like but let me yeah you could have like done it like with root of two, like like the elements of the sequence could like here's like a very silly one just to make it more clear. Like you could have had like root of 2 plus 1, like root of 2 plus 2, and you see like I'm just increasing like one element to the other by one, right? Just to make it fast, like to identify the pattern. So here in this case, again, this would be first element, second element, third element, fourth element, fifth element, and again there's kind of like you know this would be what? Root of 2 plus and minus 1. Would that work? Yeah, it's just like the amount that you add by is like one less than the integer, like the number here, right? Um, and sometimes you can start the sequence at 0. That's totally, I mean, it doesn't matter if you had wanted to start at 0. Sometimes it's more convenient to start like to call like the 0th element in the sequence, like but I just will go with like it's kind of 50-50 how you want to do it, but I'll just go with like starting the sequences at 1. It's not the end of the world. We started with 0, like like that's fine. um is that okay? So far so good. Now that's kind of like one presentation of each of these sequences, right? Which if you want, you can think about it as being like an explicit representation, because I'm literally giving you like the formula that you have to plug in to generate the nth term of the sequence. So this is kind of like these two are kind of like explicit versions of the of the sequence, right? Sometimes, and this is actually very much like the case in computer science and other things like that, where you kind of like give it more like as a recursive definition. Like, so I don't give you like a formula for the nth term. I just tell you how to find the nth term in terms of the previous term. So for example, let me do it for another way to to list the sequence, it is via a recursive definition. So here's like an example, like which you'll see corresponds to the previous two ones that we had. So a recursive definition could be saying, the first element in the sequence is going to be 1. And after, what is the formula for the nth element in the sequence? It's going to be twice the previous element. Okay. So what this is saying is that this is kind of like the where you initialize the algorithm, or like the list, right? And then you tell the algorithm, okay, to compute the next term, you go back to the previous one and just multiply by 2. And so you see, like, that kind of like pins down the sequence entirely, because what is A2? Like, just kind of to show you how that works. What is A2? According to this formula, it would be 2 times, right? A2 minus 1, which is 2 times A1, right? And I did have to give you like the original value, right? Which was 1, the initialization value, if you want. Like, that's where you initialize the sequence. So that gives you 2. What is A3? That gives you 2 times 3 A of 3 minus 1. So it's 2 times A2, that's 4, right? And you kind of see that you're kind of generating the same like elements as before, right? Like you're going to get 1, 2, 4, 6, sorry, 1, 2, 4, 8, 16, 32. The thing is, like, sometimes, you know, in the ideal world, kind of like, this is kind of, wouldn't it be nice to have like this formula always, but sometimes it is just like more convenient or more easy, like, to give like the recursive version of the formula. That makes sense. I mean, there's this Fibonacci sequence that everyone is obsessed with in pop culture, like, it has like all this, that's like a cute formula for, I mean, a cute sequence. I mean, there are like so many sequences that you can write. Like, now, kind of like as a philosophical point, it is useful to understand that not you don't have to think that every sequence has kind of like an explicit formula in some precise sense of the word. So I'll write one that I don't think you wouldn't recognize, because I mean, there shouldn't be kind of like a pattern. Sorry, like, oh, let me put it like this. Okay. Okay, so I'm giving you that list and you are like, okay, what is that? Not super clear what's going on here. So that's it. Well, I mean, so yeah, this is A1, A2, A3, A4, A5, A6, A7, A8, A9, and then you are okay. What is that? That is the decimal expansion of pi, right? So sorry, yeah. Oh, yeah, yeah, like this, you mean? Uh oh, like, move like this to the middle. You mean like, oh, got it. Like that, this kind of is centered. You mean, yeah. No, yes, for sure. So let me see. So that those numbers correspond to the digits in the decimal expansion of pi. Like, pi is like 3.1415, like, So this so here a(n) is the nth digit. Well, after, like, in the decimal like expansion of pi, after ignoring the 3, right? Because pi is like 3.14 something. right? Because pi is like 3.14. I mean, that's why I went to the computer because I was trying to go to Wolfram Alpha to find what were all the digits. There's like a person who knows like the first 100 digits of pi. I don't know if they're still alive, but for some reason, someone thought that was a fun thing to memorize. But yeah, like no, there's some like this math like people with great memory that do like memorizing those concepts. Um, So like, if you, I'm just saying like something like that does define a sequence. It's just that in this particular case, you're not going to find like an actual formula for the nth term. You know what I mean? In a sense, like that's kind of what it means for pi to be irrational. The fact that pi is an irrational number means that kind of like there's no like the sequence like the decimal expansion doesn't like repeat itself. Like a rational number has like a decimal expansion that repeats itself, like an irrational one does not. So there's not like a formula kind of like analogous to the other ones, that you could find, but it's still like a sequence, it is well defined. You can always talk about the next element. And but you need to like, to find it, you would need to do like a Taylor, like, like there are ways to approximate pi, but but it's not like you're not going to find like a formula like a sub n equals this. Like, like you have ways to find them, but not like as in such an explicit way. Yeah.
Like, when does like a sequence not a sequence? So if I just have like a random list of numbers,
No, that's the thing. Like
so
right, like the only requirement for something to be called a sequence is that you can say this is the first element, this is the second element, this is the third element, this is the fourth element. It does, but it doesn't have to satisfy any pattern, like, that is kind of like comprehensible to us, if you know what I mean. So, in fact, like there is a sense in which most sequences don't have a pattern. That's actually related to this complexity theory in computer science. Like, like most sequences don't have like a formula in a sense of the word. Like you can make that more precise, but it's kind of very special. Like if you can find like a formula for a sequence. But yeah, but that's why I wanted to give this example, because the only requirement for something to be called a sequence is that you can say this is the first element of the sequence, this is the second element, but they don't have to kind of have any like how the first and second and third elements are related to one another. That's up for grabs. Like, of course, like the ones that we will work with, they will be nice formulas for them, because that's the only way you can really tell something about them. But there is a sense in which, like, they're like, most sequences don't have like a formula of that sort. Um, but in fact, like one of the reasons is that you can use sequences to list all the real numbers. Uh, because like a real number is like a number followed with a decimal expansion. So you can in like every real number can be represented by a sequence in a sense. And I mean, like if you ever take discrete math or something like that, you will find out that they're more like real real numbers than natural numbers. So you cannot really like the totality of them cannot like be understood in the same way. So like there's but anyway, so this is just to show, this is just to show that uh any collection, right, of numbers gives a sequence, gives rise to a sequence, provided that this collection is listed in the way that I mentioned before. Gives rise to a sequence as long as this collection of numbers can be listed, as long as we can list those numbers. By the positive integers. Oh, sorry, yeah. I mean, the thing is, right, like, it's kind of what I was saying before, like you can make a different convention, but like kind of like the idea is that the list kind of like goes on it like forever in one direction. If you were to think about indexing something by the integers, you want to say, oh, okay, this is like the zeroth term, the one term, the negative one term, the second, kind of goes in both directions to infinity. You know what I mean? So it's kind of like a it is kind of like a sequence moving this way and then another sequence moving that way. But that's not how we're going to, it is not as convenient as just like the sequence per se, because when we talk about limits, we will talk about limits of sequences, and that is kind of like, if you had integers, it's kind of like doing it with at infinity and minus infinity, whereas like we would just do kind of like the limit at infinity in some sense of the word. Yeah.
Terms of sequence can be happening, right?
Oh yeah, yeah, right. Oh, yeah, exactly. In fact, like here's like one like here's another sequence. Yes, yes, yes. So yeah, because I have only given positive examples. Sorry about that. Here's another sequence. You could do like one negative, like the light switch sequence, on, off, on, off, on, off. One negative one negative one, um, one negative one. Like it just flips between back and forth between one and negative one, like up, down, up, down, up, down. And so yeah, like this is like a sequence, and in this case, what is the formula? It's like -1 to the n, I guess that would work, right? Because it's positive whenever n is odd, right? Like if this is A1, A2, A4, A5, A6, it's positive whenever n is odd, and it's negative whenever n is, sorry, yeah, yeah, whenever n is, okay, so I did it backwards, right? So, oh my God. So yeah, yeah, like plus, let's add +1. Now it fixes it. So like that is like, now, yeah, like, because now if you, for example, like you need it to be positive at odd numbers, so like, the next, this has to be even, you know, uh, you kind of have to work it out for yourself, so, because like sometimes like the index thing, like the shift can be annoying, like, which is why sometimes people prefer to start at zero the sequence, you see, like that could save you some like headaches. Which, by the way, does give you the same formula as -1 to the n-1, right? Like it will kind of have the same result. So it's kind of like also useful to understand that even if you have like a formula for the sequence, it can be presented in different ways, and still represent the same list of numbers. Oh yeah, sorry, yeah. Oh, because like like I'm just saying, like you could, like you could say, okay, I have like a collection of numbers, right? But, or I have like a collection of things, right? But what makes it like a sequence is that I can say, oh, this is the first element, this is the second element, this is the third element in that collection. Like, that you can kind of like put like a post-it note that says this is your number, right? Like that, and that number has to be a positive integer. You could have situations where like maybe, like back to what we were talking about, like whether you could use like negative numbers, right? So you could have said, oh, this is the third element, and this is like the negative second, like -2 element of the collection, right? Like, so like the numbers that you use to refer to that collection are like both positive or negative. But like on a sequence, like, the list is only like first, second, third, fourth, fifth, sixth, seventh, eighth, it doesn't go both ways. That's what I was trying to say. Is that making sense? Yeah.
Also, is this like always infinite? Like, does it always have infinite upward here?
Oh yeah, yeah, no, it can, yes, it can kind of become constant eventually, but it kind of like the idea is like it goes on forever, like, so it never terminates, yeah. But it can like, yeah, like it can, like, here's another example. Oh yeah, maybe I wanted to switch back and forth, and then I just got tired. I was zeros like after that. Like, so of course, if you wanted to describe this as a as a sequence, uh, it's kind of like better to do it like explicit, a little bit, kind of like a hybrid between explicit and like a formula. And then you say, oh, for it is 1 for n equals 1 and 3. It is -1 for n equals 2 and 4, and then 0 for n greater or equal to 5, right? And that kind of like pins it down. Because if you were to try to find like a formula that, like kind of like a single formula that worked for all the terms, that's a little bit more complicated. So you don't have to make your life harder than it needs to be. But yeah, like we don't think of the list as being a finite list. So but sometimes like it could kind of like just like keep repeating, like or like do blocks, like where you kind of like then repeat this pattern and then it complete, like there's so many possibilities, but you do want to think of it as going on forever, um even if the numbers themselves like are just like a finite collection of those. Yeah.
Series like this can't be written with like an equation, you have to split it up.
Right, a sequence. I'm just to clarify, because we then have to talk about series, which will be a particular type of sequence. So yeah. But yeah, like sometimes there's not like a single formula. It's kind of like the analog of a piecewise defined function. Like maybe just to kind of like, it's kind of like, what is a sequence? It's a discrete version of a function. Like if the word discrete rings a bell. So it's kind of like a finite, it's kind of like a function kind of like changes continuously because x can take any value. Here, like the sequence kind of like takes jumps, it's kind of like a jump version of a function. Okay, so this is kind of like analog of piecewise defined function. Sorry, just to go up. Okay. In fact, like now that I brought up the word function, like there are kind of like somewhat graphical representations of a sequence you can do, and here's like a way to represent the value, like the sequence, you know. So here's like a graphical. So you can take like kind of like think of kind of taking the horizontal axis as kind of like the x-axis, but you just focus on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So I'll kind of draw like the xy plane. So here's 1, here's 2, here's 3, here's 4, here's 5, here's 6. And so on. And then the sequence kind of like A1, maybe A1 is here, maybe A2 is here, A3 could be negative, so it could be here, A4 could be here, A5 maybe it is like higher, and then A6 maybe it's like at the same level as A4. So it's kind of like it's kind of like, again, in this case, it does look kind of more similar to how you would draw the graph of a function, right? It's just that for the graph of the function, you kind of plug in the function at all possible values for x. And here for a sequence, it's just like a value 1, value, like, 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay. So like just to make it more concrete, what is like for like let's do that for a sequence an equals 1 over n actually. So because that motivates like something here, like an idea. So a1 would be 1, a2 would be 1/2, right? A3 would be what, 1/3? A4 would be, I mean, I actually should draw them more like kind of like as a hyperbola thing, you know. A4 would be 1/4, and like, you know, here's 1, 2, 3. And so AN is like, sorry, AN would be somewhere in here. Oops. And like in this graphical representation, like as you can see, like, you know, like the dots that represents like the different values for the sequence, like the different elements of the sequence are getting closer and closer to zero, right? So you would like to say that as n goes to infinity, the limit of the sequence is zero, right? So you would like to write something like, so want to say that the limit as um n goes to infinity of 1/n is just zero, right? Oh, let me add an extra step, like the limit as n goes to infinity of a sub n, but a sub n in this case is 1/n. Yes.
The graph is just basically those points at like intervals of integers, so how is the limit even defined? Isn't it just like all the same?
Well, the like, what does it mean? Okay. Here's one way. I don't, let me kind of answer your question without kind of like going into the actual definition, but you know, um, this is what is called like the epsilon delta definition, like, you know, of a limit. But what you say, like in words, what does it mean that all the elements of the sequence? So what I'm like, again, I'm not going to ask like the limit definition. This is not something that we do, but um, when you say the limit of a sequence is like a number, right? If you thought about the limit being L, you know, think about it kind of like how you would think about it in calculus, like kind of like as a horizontal asymptote. What does it mean to say that the limit of a sequence is L? It means that eventually, you know, the sequence can be doing its own thing, it can be doing whatever it wants, but eventually it has to kind of like get close enough to the value of the limit. You know, it has kind of to stay within some like bandwidth of the limit, which is kind of like this epsilon thing that I'm talking about. So there's kind of like a safety zone, you know, and eventually all the elements in the sequence needs to be contained in that safety zone. This is what, like, you know, if you take real analysis, like you would kind of like go over all this. Like, it's very fun actually, but like, you know, it's kind of like there's a safety area and eventually you have to enter the safety area. But how big is the safety area? It can be as small as you want. That's kind of what makes it. So you always give yourself some safety zone, but you are allowed to kind of like shrink it as needed. So that's kind of like what makes it work. But in practice, we will find, don't overthink it, because like the way we'll find these limits is like in the same way as you would find the Calc 1 limits, like, or like it kind of like works more or less as a limits of like a function at infinity, like the same rules basically apply. Because like the sequence is kind of like in that sense, it's kind of like a special case when like you're just looking at the integer values, of like a function if you want it. Um, oh, sorry, yes. Oh, yeah, sorry, that's the letter epsilon. Yeah. So it's kind of like saying that, so sorry. That's kind of like the naming calculus for all these things. So like the idea is kind of like this safety zone that I was talking about. It has like length epsilon on each side. Sorry, I think I should have like made that picture more clear. But again, don't worry about that because I'm not going to ask like for that definition. We're not going to use it or anything. But it's kind of like if you say, for example, that the limit is 2, that means that eventually you have to be super close to 2. How close? Like within some error. Like you can think of epsilon as some sort of like error or like distance. So within some distance like of epsilon to the limit. Um, that okay? Is that making sense? Now, in practice, what I was saying is that in practice, in practice, we can find these limits more or less in the same way as you would have found the limits of at infinity of a Calc1 function. So in practice, we can find limit as n goes to infinity of a sub n in basically the same way the limit as x goes to infinity of f of x for in Calc1. So when you're computing these limits, it's almost like useful to think of the n as being x and just ask what does the limit would be if you replace n with x, and that more or less gives you the correct answer. So just to give like let me give you a few examples. So what would be the limit as n goes to infinity of n squared plus 1 divided by 3n squared plus n, right? So again, if you kind of compare, like what I'm trying to say is that you should compare with the limit as x goes to infinity of x squared plus 1 divided by 3x squared plus x. It is like if they more like basically will have the same answer if the limit exists. And okay, in Calc 1 there were a few clever ways to do it, like like if you know L'Hopital's, you could even have used L'Hopital's to find that limit, but it's not necessary to kind of like do something as strong as L'Hopital's. Like you can just factor out the n square in the numerator and the denominator. That's probably how you first learn how to do that anyways. So if you factor out an n squared, that gives you 1 plus 1 over n squared. And this, if you factor out an n squared, that gives you 3 plus a 1 over n. And what happens next? Like the n squareds go away, right? So it's 1 over 1 plus n squared. So 1 plus 1 over n squared divided by 3 plus 1 over n. But in this presentation, it's a little bit more clear, what the limit is, because these we already talked about, like 1 over n is basically 0 at infinity. And 1 over n squared is also like 0 at infinity, like, more or less for the same reason. So that becomes 1 over 3. But this is like so far so good. Here's another one. sine of n over n as n goes to infinity. Again, I'm saying here that you, when you're computing this limit, you can compare this with, if you like, compare it with, so anyone, like, what was the limit in Calc 1? Anyone remembers this? Zero, right? Because and what I do like about this example, which is at least it's not L'Hopital, because for L'Hopital it has to be infinity over infinity or 0 over 0. Like the sine of x has no limit at infinity, right? So it's more like a squeeze theorem thing, because the idea is that sine of x is always between -1 and 1, right? And then you divide by x and that squeezes everything, right? So what you would have done here is that you say that, notice, and so I'm just trying to kind of show you that like this limit, like for sequences, well, at least when you're trying to find limits, many of the things are like they are identical to what you did in Calc 1 with limits and infinity. Um, okay, and then the squeeze theorem says that, so this is zero as n goes to infinity, right? So makes sense. So far, so good. Questions up to this point. Okay. So now, and I will say a little bit more about sequences on Wednesday, but there's like a very important type of sequence, which is like the main focus of this course, which is called a series. So this is like the master sequence. So this is kind of like the most interesting sequence that we can study. So it is kind of like, at least it takes a little bit more time to absorb. So I want to kind of mention it today so that, like, um, so it's like going to be a very special kind of sequence. Did I send you this announcement about the video about Zeno's paradoxes? I don't know if everyone got a chance to see it, but it's kind of like this. There's like this Zeno paradox of motion, like from ancient Greece, like of why Achilles can never catch a tortoise. So, which is it's fun to watch the video, but basically, at least for us, what it boils down to is kind of like saying, I mean, I'll kind of like illustrate it in person. It says, like kind of like the version is like to say, okay, I can never get to that door. If I would try to walk to the door, I actually am never going to finish. Because first, like say if this were 2 meters, well, which is not, but just for sake of like the numbers coming out nicely. First, I have to walk half the distance. So if I walk half the distance, I'm here, right? Then I have to walk half the distance of the remaining distance, right? Like so now it's 1 meter left, so half a meter, right? Then I have to walk half of the remaining distance, it's a quarter, right? And then half of the remaining distance is 1/8, then 1/16, right? But when am I going to end? There's always like some non-zero distance left over. So it seems like we're doing like, they are getting shrinking, right? Clearly, because it's half of the previous step. but there's always something else that you can walk, right? And so, one, one way to think about it is that, if you kind of like add up my steps, I did first 1 meter, then half a meter, then a quarter, then, and like, then an eighth. So kind of like, the sinus paradox. I mean, there are actually a few. There were like there are four classic ones, but it's something like, what do you, I mean, if you want to rephrase it in kind of like a way that's kind of motivating for calculus, is like, what do you get if you do 1 + 1/2 + 1/4 + 1/8 + 1/16 + 1/32 plus, right? Like, what if you kind of keep adding like a number plus a number plus a number plus a number, but they kind of like, the next number is like half the previous one. Uh, so I mean, the dots, right? Like, of course, that's not super precise. Like, the idea is to turn that into a limit, at least for us to kind of like handle it. Here's another one that, like, so this is like one type of, like, this will be called a series, by the way. So a series, this is going to be a series. So a series is going to be like an infinite sum, basically. So a series is going to be an infinite sum. Here's another, I'll kind of write some classic examples of series, like, and then I'll kind of show you how we kind of can attack, like, understand them, like, using this stuff about sequences. So here's another one that's so this is like kind of like, I mean, this one will be called like a geometric series. This is going to be like a geometric series. Here's another one. If I do 1 + 1/2 + 1/3 + 1/4 + 1/5 + 1/6 + 1/7. By the way, I at least, I don't know, like, at least hopefully it is clear that there's a sequence hidden in the picture, like, because there's a sequence that you can use to tell me what these elements are, right? So here, that you could say that is 1 over 2 to the n minus 1, for example. If you want to start the sequence like at 1, okay? And sorry, this keeps going, right? And of course, there's a more fancy way to write this down, but I'll get to that in a second. Here's another one that, you know, so the difference with the previous one is like, it's like just 1/n, right? Like, and this one is called like the harmonic series. And the numbers that you add don't need to be all positive, by the way. So here's like one that's kind of like fun. Um, Here's another one. I don't think this one has like a particular name. So you can do 1 + -1 + 1 + -1 + 1 + -1 + 1 + -1 dot 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 dot. So that one is kind of fun. Yeah, I don't think that this one has a name. But here's another one you could do. Like, you could do 1 - 1/2 + 1/3 - 1/4 + 1/5 - 1/6 + 1/7 - 1/8. So I don't know. Hopefully this one at least like the pattern compared to the previous one is clear because they're the same kind of like numbers as the ones that you had in the harmonic series. You're just like switching the sign of like flipping back and forth. Um, so it's like, you change the positive to the ones that have like even denominators, right? And this one would be kind of like an alternating series. Okay. Okay. And what makes this interesting, what makes this interesting is that, as you might expect, kind of similar to improper integrals, actually, this is very related to improper integrals. Because an integral is like some sort of sum, right? If you think about the Riemann sums, like the rectangles that you use to approximate the area. So an integral is secretly related to sums. Here we're going to do sums or like adding things together. Oh, yeah, sorry.
It's like what we did for like the expansion of five, we sum that all up, would that also be series?
Well, okay. So there, well, if you were to, right, like, yes, like just to go back, I think I know, see here, you're talking about these integers, right? If you were to, okay, so, right, if you add those on the nodes, right, if you add them directly, you cannot recover pi. If you want to recover pi, you have to do like the decimal representation, which is like divide by the powers of 10. Which is like, so it would be 1/10⁻1 plus 4/10 squared plus 1/10 cubed plus 5/10. You know what I mean? And that would count as a series. I mean, you have to add the original three because it's 3.14, whatever. But yeah, like right, like if you take the decimal expansion, you can turn it into a series that does give you the actual number. And that's actually how you switch a number from like decimal to binary, like other things. Right. The one that I was going to mention, well, what I was saying is that, so like a series is some sort of like, because a series is some sort of like infinite sum, it will be related to integrals, improper integrals, because like the improper integrals were from 0 to infinity, right? Like these are kind of like sums that go up to infinity. Then, what happened with proper integrals? Sometimes they were finite, sometimes they were infinite. So sometimes this series will converge, other times it will not converge. Like meaning you will get a finite number, and other times you won't get like a finite number. Like one that is like a really cool example. So so uh so sometimes the series will be finite, and that way we'll say converges. In the otherwise it would be called divergent, a divergent series. Um, like a crazy example of this, which is kind of like unexpected, is like there's this really clever formula for pi squared over 6. Um, so which is kind of like crazy because how, like, I'm saying like take an integer, square it, put the number in the denominator, right? So like square of integers. The denominators are the squares of integers. Are all these like, so like, add the reciprocals of the squares of the integers. I mean, you could even write this as 1/1 squared if you want to kind of like make the formula look like identical in every step, you know. And supposedly that should give you like pi squared over 6, which is like, which is again, of course we were not going to prove this. Like actually that's like a difficult thing to prove, but I'm just saying uh you can end up finding very weird formulas that you wouldn't have like imagined that you could find. Like, um so but kind of what I have to tell you first is like how to first like some proper notation for all this stuff, and then like how we're going to think about this series. Um, okay. Does everyone remember, like, have you seen all, like, the sigma, like, the sum notation? I will say it again anyways, what this is, but it's kind of like a very nice way to refer to, like, a sum. So there's, like, this sum notation, which is called sometimes, like, the sigma notation. And so, well, we can, thanks to the fraternities, you recognize the letter sigma, right? So that's sigma from, like, like sigma, kappa, beta, alpha, whatever, So, what this means is, like, sigma stands for sum, so it means the following. Oh, sorry, I'm supposed to start at one. Um, so what this notation means is, oops, A1 plus A2 plus A3 plus A4 up to AK. So it's like a very nice way to write like the sum of the first k elements of a list of a sequence. Like that's why sequence is very important here. So here A sub k is a sequence if you like. So here A sub k is some sequence. All right. Well, A sub A sub n is a sequence. And the idea is like this notation is just like a notation for adding the first few elements of that sequence together. So this is like adding the first n elements of, oh, sorry, that should have finished at, this should have been n. Um, so just to kind of like, maybe I should use different colors. So like these two are supposed to match. And these two are supposed to match. So this tells you where you start the sum. Like usually we will start the sum at one. Sometimes it's useful, like meaning like the first element of the sequence. Sometimes it's useful to start at a different spot. So this kind of like tells you what is the first number that you're going to put here. And this tells you what's the last entry that you're going to put here. So for example, like just to make this a little bit more precise, like more concrete. What if I said I want to do k equals 1 up to 3 of you know is n squared. So sorry, k squared. Oops. Oh, sorry, yes.
Say here, and it's a sequence to be, and it's like the general term.
Right. Like an is kind of like the nth term of the sequence, yeah.
Is that basically the formula which we use to like define the sequence?
Right, like for example, yeah, like it would like yeah, you can think about it in terms of like the formula that we use to define the sequence. So for example, like here, like the sequence like I mean, like you don't have to think about it in terms of sequences right now, but it is a bit like more convenient later on. but once I give you specific numbers to everything, you can kind of forget about the sequence. What it's saying is that you have like this formula at k squared, right? You're going to replace k with 1, 2, and 3 because it goes from 1 to 3, and and so you're just going to plug in these values of k and add them all up together. Sorry, you're there like notation. You want to like just count every other number? Or... yeah, there are actually like for example, well, it depends. Like for if you wanted to count like I mean yes, like not that we're going to get into those like minutia, but like yeah, for example, if you just wanted to count the even numbers, you would put a 2k here, replace the k with 2k, and that kind of like keeps track of the even elements of the sequence. No, like there are ways to do that. Yeah. So this would be 1 squared plus 2 squared plus 3 squared. So it's like the sum of the first 3 squares, like the first 3 squares of integers, like, and that's like what 1 plus 4 plus 9, which is 14. In fact, like let me see. Just want to make sure I don't have it wrong. Okay, yeah. And so and then for example, if I had replaced k, if I had put 5 here, a squared, that would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Well, we already know what these first 3 add to because that was 14, right? So it's like 14 plus 16 plus 25. That's not such a bad number, right? That's 55, if I'm not mistaken. Is that making sense how I'm generating the partial sum? And then there's like a very elegant formula for like actually there's like a closed formula for the sum of the first n squares. Like I mean probably it was Gauss who found it because he found all these things, like all this like number theory stuff. So or Euler, like those two like basically found everything when it comes to like this like stuff about sequences and series. But if you add the first n integers, again, like so this is what this stands for, but you see like how the sigma notation is so much more elegant, right? But that is literally what it's computing. Like it's computing the sum of the first n squares. But like it is all being summarized here. So it's kind of like a way to avoid dot, basically. So like the formula is yeah, it just was wanted to make sure that I didn't like spoil it because there it is. Like that's the sum for the first n squares. I mean, there are ways to prove this. Like one is induction. Like there are different ways to do this, but like not that we're going to get into. I'm just trying to illustrate to you how like just getting used to the notation. Is that making sense? Just up to this point. Okay, and now now that I have told you a little. By the way, notice that this should be related. You should think about this like. Look how similar this is to an integral, like the notation, like so right, compare this to or something like that. That's what you should really compare with. So this is kind of like the lower bound, this is like the upper bound, and this is kind of like the function that you are adding, like the stuff that you're adding. So like this is kind of like the continuous version of like this formula in some way. So like they kind of play similar roles, like because again, like an integration is some sort of is a sum of sorts. Of course, like wouldn't be the same number because like like the integral is kind of like continuous. So like you're adding like infinitely many terms. So here, like this is like a finite sum. But just to go back to the series, like going back to the series, so how are we going to think about this? Um, so if we kind of like do this geometric series, like, and next time I'll kind of give you all these definitions, you know. Just to make the analogy more clear, and hopefully this will help. Um, Let me put this here. Here, this is like the analogy you should have in mind. What was an integral from a to infinity of f of x dx? That was a limit as b goes to infinity of a to b of f of x dx, right? And I'll be even more clever, and I'll call, instead of calling this b, I will call it n. So it's like the limit as n goes to infinity of that finite integral, right? So we're going to do something similar. So what we did here is kind of was truncating the series, like the integral, right? You wanted to integrate up to infinity, you kind of like stop at a value n, and then you let that go to, then you take the limit. So we're going to do the same. So I'm not going to try to add all these numbers directly. I cannot, because there are really many. I will stop at the nth term at the first n. That gives me something that depends on n, and if the limit exists, that's the value of the series. So what I'll do is kind of like do a truncation. So truncate. So you can check, like, hopefully like this makes sense, like from this sigma notation for the sum. If you were to put k equals 1, k equals 2, k equals 3, k equals 4, up to k equals n, you will get like this, like first terms. Okay? This is going to be called like this. Okay, but and then you define the series, and then you would like to take the limit of as n goes to infinity of this, and so we want to define Momosta. You want to define this as a limit as n goes to infinity of what I just wrote. Okay, so you kind of add the first few terms of the sequence up to like the nth term. That's going to be called like a partial sum. So like I'll just at least tell you the name for that, and that's where I'll restart the next class. So this is called a partial sum. Okay, and so the idea is that in general, like just to kind of like and I'll finish here and I'll kind of repeat some of this like again, but at least I want to kind of like leave you with that thought for you to like meditate about it. So like the idea is that you want to say that A1 plus A3 plus A4 plus A5 dot 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 plus AN dot 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 dot, right? Like the series of all these elements, it is a limit as n goes to infinity of k equals 1 up to n of a sub k. Okay, so this is how you want to think about a series, which eventually will be written down as as a shorthand notation, just like this. But so and I'll repeat this like next time. But the idea is that we are going to have like a kind of, we start with that starting, we have a sequence. Those are the terms that we're adding. We're adding the terms from that sequence. And we add like a different, we stop here, then we stop here, then we stop adding here, then we stop adding here. So that gives you also a second sequence of partial stops. So there's two sequences that are going to be explained. The sequence that you're adding and the sequence that keep track of the value of the sums that you're getting. So that that can be confusing, but we'll kind of work it out in detail on Wednesday. And Wednesday will be the last day we cover material for the exam. So yeah, again, like tomorrow I'll send you like a study guide for the exam. But whatever we do on Wednesday, that will be it. Okay. I'll stop here because we already talked a lot about
A study guide?
I'll send it tomorrow. Yeah, yeah.
Study guide from you or a study guide from general?
The coordinator will send his today, actually.
You said what? Sorry.
The coordinator will send his study guide on today.
For like all of math.
Right, like you will get like kind of like from this canvas, all section side, you will get like kind of like the topics. The thing is like, I'm not sure if I will get to cover everything that is supposed to be on the exam. I know already do like
Already have lost in the rush.
Like that in class.
yeah, because I do the stuff very similar to the stuff we do in class.
I realized that last time. I'm like, yeah.
No, like I mean, yeah, I'm good, but I do like if you kind of notice, I did take like a problem, literally, basically copy pasted it from like the problems that he sent. So I will always kind of like take one from them, just to go to them and like, yeah, but they're like, but yeah, it's always better to kind of start with like the one that I'm telling you to prioritize them. But I will kind of like take one from this, and kind of like motivate everyone to go through their time.
I didn't,
Let me stop like the recording.
I didn't submit the, I don't know how that works.